YouTubers, welcome to yet another interesting video. In this video we'll be looking at mass and weight. Mass and weight. We notice that any object that is raised up, once the support is removed, will come down. So let's see. Raise your balls up, remove your hands, raise your balls, and this is my crumpled paper. If I raise it up, it must go down. Now the question is, why is it dropping down? Why are they all coming down? We are looking at the reason why they are coming down. Hey, Gerald, sit down, sit down, sit down. So we notice that whenever support is removed from any object, that object will fall down. And this force tending to pull the object down towards the earth center is what we call weight. Let me take it again. When the support is removed from an object, if I remove my hand now, the object falls down. And that force tending to pull this object down towards the earth is what we call it. The force tending to pull the object down is what we call the weight of the body. And then the force with which the earth attracts every object towards its center is called gravitation. And this gravitation work was done by Newton. When an apple fruit fell from the tree, fell on him, and then he received a blow, and that blow made him to think, and then he started his work on gravitation. We will now carry out experiments to now know how the gravity pulls every object towards its center. To measure weight, this is spiral spring. Spiral spring. When the force is added on it, you notice that it will stretch. And when the force is removed, it goes back to its original length. And when you're adding force, if this is weight, I want to add on this, the force I want to add on this spiral spring, when I am removing my hand, you notice that it keeps stretching. It keeps stretching until an equal and opposing force is set up, then the stretching will stop. Let me do it again. You see that it has gone back to its original position. Now, if I'm removing this support, I'm giving to this weight. If I'm to remove the support, I'm removing it. I keep removing, I'm removing, and then my hand is off. Now, this stretching has stopped because there is an equal opposing force that is already set up on this spiral spring. That's why you see it has stopped stretching. Then we now want to carry out an experiment to show that the earth attracts every object to its center with equal force. Let's do this experiment using spiral spring. And spiral spring, this property of spiral spring is utilized in spring balance. This is spring balance. And spring balance is used to measure weight. You use it to measure weight. This is spring balance. You use it to measure weight. All right. So we now go to the experiment. Here we have our weighing pan. This is our pan that we carry our weight. We have the spiral spring here, and then we have our pointer. So when we add our mass, the weight, first of all, we start with 50. And again, you have to take note the original length of the spiral spring. What's the original length? We have the original length of the spiral spring. You have it around this 43. Can you see it? So 43. Now, when you add 50 gram mass, 50 gram mass, now read it off and tell me what it will be. Look at it. Don't hold the down. Just guide your pointer to the meter rule. 46.5. Yes. 46.5. Now, record 46.5 minus 43. Then you add the second mass, and then allow it to spring. Allow it to spring. You can actually stop it by doing this and then gently removing your hand. Then this is, you now reach. You can say 50, 51. You remember your pointer. Make sure you always allow your pointer to point. This is around 50. This is 50. Allow your pointer to point where 50. Then you put the second one. This is what now? This is 150 mass. 150 mass. Allow it. You can stop. This is around 53.5. Around 53.5. Then you now put the 200 gram mass here. Turning. You're not supposed to keep it straight. We have around 57. Around 57.0 minus 43. Then when you now do the calculation, 46 point, we said 46.5, 50.0, 53.5, and then 57. Now, the results of our experiments. Here, we already have that 50 gram gave us extension of 3.5. 100 gave us 7.0, 150, 10.5, 200 gave us 14.0. And then looking at this last column, the extension all over weight, we have 3.5 over 50 is giving us 0.07, and 7.0 over 100 is giving us 0.07, and then 10.5 over 150 is giving us 0.07. Likewise, 14 over 200 is giving us 0.07. This shows that extension increases proportionally to the weight causing it. Extension increases proportionally to the weight causing it. And this tells us that the gravitational pull, the earth pulls every object to its center with the same force. We now go to look at the other aspect of the gravitational force, the gravitational pull of the earth. It pulls every object with the same force towards its center. But the weight varies with the position of bodies. The weight varies with the position of the bodies. Why will the weight vary? The weight, when you weigh a mass, when you weigh anything, a body, at the top, on top of the mountain, you will notice that with sensitive instrument, it will vary slightly when you weigh it at the bottom of the mountain. Let us now use the globes and then some other things to explain, to let you know why the weight varies and the weight is not constant everywhere. It changes as the position of the body changes. We want to now show why we have the variation in gravity due to its position. Variation in gravity due to its position. When a body is changing position, we notice that the gravitational pull also changes. Now this represents our globe. This represents our globe, and here we also have the globe, but I'll focus on this, use this to point out certain things. Now, we have this round ring here, this round ring representing our equator. This green one is your equator. It is at the center of the earth. Again, you have the longitude. This green long line is the longitude. Also, looking at this orange is representing our globe also. And this orange is not perfectly spherical. We know that the earth, because the earth is not perfectly spherical, you now have, if you remove one of these, you now see your longitude. And this longitude is like this line here. It divides the earth into east and west, while the equator divides the earth into north and south. Take a look at here. This is the polar axis. This long line cutting across is the polar axis. And from here, from this center, this is equator, this is the center of the earth, we now have this green line coming to this place. You look at this green line coming to meet this equator here. This is the radius of the earth. The radius of the earth. When you now watch closely, you now see that some countries are here, and then this is the latitude, longitude, and then latitude. All these ones are latitude. You look at here, from this center to this latitude, can you compare the radius and this radius? You notice that this radius is bigger than this radius. Look at this ring, this latitude, see the diameter is smaller than this, smaller than this, smaller than this, smaller than this one. This equator diameter is bigger, and then the radius is also bigger. Now we see that the radius at the equator is higher than the radius towards the poles. The radius here, between here and here, you notice that here is higher. And then looking at the formula is put up there for you now. G is equal to capital G times the capital G is the gravitational constant times the mass of the earth all over the radius of the earth squared. All over the radius of the earth squared. And then when R is dividing, and if R is big, which means G will be small, and if R is small, which means G will be big. And that explains why you have the countries near the poles experiencing higher gravitational pull than the countries around the equator. I hope we are getting this. Now, look at this globe. You can watch closely. See the longitudinal lines, and then see the latitude, and then look at the equator. The equator is the middle. The center is the equator. The center is the equator. The center is the equator. So this explains why the position of the body varies. It's not constant at any point or any place around the globe. Freely falling bodies. Freely falling bodies. Let's see what will happen. Now, I have crumpled paper and uncrumpled paper. Let me release two of them and see which one will hit the ground first. And then here I have the feather and the weight. I have the feather and the weight. Let's see. Now, Aristotle, the Greek philosopher, initiated this idea, the discussion on freely falling bodies. He believed that the bodies, the heavier bodies, will fall first before the lighter ones. But Galileo did not agree. Galileo now conducted an experiment from the Leaning Tower of Pisa, where he used different masses of iron balls and he released them. From the experiment, all of them struck the ground at the same time. Now, why is it that we are not able to experience this? The feather and the weight. We are not seeing them falling at the same time. We have what you call air resistance. Air resistance. Because of air resistance, the bodies are not, the air is resisting the lighter mass. That's why it's not falling at the same time with the heavier one. But when this experiment is conducted using a glass tube, when you extract all the air, leaving it to become a vacuum, you now notice that both the feather, the uncrumpled paper, the crumpled paper, and then the mass, all of them will strike the end of the tube at the same time. And then, so this is showing us that air resistance is responsible for us not observing this. So when you throw the feather and the coin at the same time, you notice that what you observe is that the coin will strike before the feather. But the reason is this: the air resistance is responsible for making the feather to delay in striking the ground. Mass is a measure of inertia. A large block of iron has more mass and hence more mass than a small block of wood. Mass does not depend upon location, shape, size, and so forth of a particular object. It refers to the quantity of matter. The more mass an object has, the more matter it contains. When you look at objects, you notice that this is meter rule is lighter than this mass, this weight. So the more inertia it has, the more mass it has, the more it will weigh. It does not vary. It is constant. And you use beam balance to measure mass. Now let's look at what happens in our chemistry lab when we are asked to measure the salt for practical experiments. Let's see. This is a beam balance. See the graduation. Here is 0 to 10 gram. For measuring the first part, you use it to measure the small masses up from 1 to
from 0 to
10
gram.
The middle one, you measure from 0 to 500.
While the last one
from 0 to 100 grams. They are all measured in grams.
So in position of this, now you can see you have a calculation here from 0 down, and whatever you are weighing, you have to start from 0 point. You have to be at 0 point before you now weigh. And this has a weight that you can hold to affect the weighing here. So you reduce whatever you are weighing with this paper from this before.
That is correction of zero error. You correct your zero error. So
zero error before you
now you have placed this. Let's have it at 0.
So at 0. So I'm having it at 0. Whatever you want, you have to balance it here first. You balance what you are having on this filter paper. So by the time you have it here, it's already at 0 point. You now come. What do you have with this?
It's balanced.
It was balanced already. So what do you have with this filter paper?
You don't really need to wait for it to just be here. You look at the displacement up and down. So you take the mean.
So by the time
now look at it. Look at it. It's now at 0 point.
Now I want to weigh 10 grams. 10 grams, you have to add whatever you have with this filter paper with this one. Or let me say I'm taking
so
like
what's the filter paper? What
the filter paper now is weighing 0.9.
0.9.
0.9.
Okay.
So if I want to weigh 9 now, I have to add it to this.
Look at it. How is it 0.9? Look at this up. You see a pointer.
Yes, it's an arrow there. There's an arrow there. You now shift it to this. For this 9 gram I want to weigh, you take it for. This is the 9 I want to weigh already. So with that 0.0 9. I
You
have to
now
shift it to this
okay.
place.
That's the
That's
correction of zero. Error.
So I'll start now weighing
Check
my.
for the balance.
Yes. So I can now be watching it here. If it's more than, you reduce. Reduce.
No, you need to add.
Add more.
You add. You add.
Yes.
This is the beam balance.
Beam balance.
Trying to use it to measure the salt. You see, coming up to 0.
To 0 point.
As it's displacing, you can see it is coming up to the 0 point. So this is measurement of mass. We use beam balance to measure mass, and we use spring balance to measure weight. And weight varies from position to position, but mass does not vary. Mass is constant. Anywhere on earth, in the moon, mass is constant. It doesn't vary. With this, we will now show you we will now want to draw the differences between mass and weight. Mass and weight. The difference between mass and weight.